We're going to talk about why should you conduct oil spill modeling, the differences between modeling for response and planning, the weathering processes that go into modeling oil, the different methods that are employed, parameters that are sensitive to your model results, and how would you go about setting up a simulation. First, who is RPS-ASA? We were formerly known as Applied Science Associates. We're now a member of the RPS Group. We're a global science and technology company. We provide environmental modeling and application development and help a diverse range of clients solve their issues of concern. We've been doing this since 1979 in over 100 countries. We're the developer of OilMap, which is a commercially available oil spill model, for 20 years. One of the things that's unique about RPS-ASA is that we're not just developers, we're users. The scientists and engineers here use the application every day. Peace, who again, thank you, is facilitating this, is a practical professional career training for the oil and gas industry, for upstream, midstream, and downstream, ranging from technical topics in engineering and science to management and communication, from a basic skill level all the way to high technical skills. Who am I? I have 15 years experience with modeling hazardous material, oils and chemicals in the water and the atmosphere. My background is in chemical engineering and environmental engineering with a focus on oceanography. I'm a developer and an integrator of model algorithms. As well, I conduct training courses in oil spill modeling. I perform modeling for emergency response, contingency plans, environmental risk assessments, NEBAs, NRDAs, cost-benefit analysis, you name it. If you have to model something on the water, the land, or the air, and you have to analyze it, I can help you out. So why may you be interested in modeling oil spills? Well, on land, the primary concern is the intersection with navigable waters, as well as groundwater contamination and socioeconomic resources. Now, that oil on land may reach the water surface or the water, or you may have a release into the water or in from the seafloor. Now, if oil is on the water surface, there can be a smothering or coating exposure to wildlife, shorelines, nearshore structured habitats, or socioeconomic resources. There's also water toxicity associated with the oil, as there's soluble components of the oil called aromatics. This can be direct on fish, invertebrates, algae, or indirect via food web. Submerged aquatic habitats, and as well as drinking water contamination. So what is a numerical model? Numerical models provide information when there's a lack of real measurements. They give another approach to the reality. They help understand and reproduce complex systems. It's used to predict the short, mid, or long-term consequences. Short-term being emergency response, search and rescue, mid-term being an environmental impact assessment, and long-term being climate change. During this talk, we're going to talk about oil spill modeling, which are short-term and mid-term numerical modeling schemes. Now, I noticed that initially when we were taking a poll to see the experience that people had in oil spill modeling, there were some new folks to oil spill modeling, and there's some folks that have been doing modeling. So some of this may be repetitive, but for those that are new to oil spill modeling, I'm going to go through just a few terms that are commonly used when you're talking about oil spill models. The first is Lagrangian. So Lagrangian is a type of model. It's when you take the total amount that's going to be released into the environment and you break it up into Lagrangian elements, commonly referred to as spillets. Those spillets are then tracked as they move with wind, currents, and natural dispersion. Weathering is calculated on each individual spillets, and the results are provided by summing up spillets. Gaussian is a statistical method of normal distribution. It's a method of distributing mass contained in spillets when you're dealing with oil spill modeling. Dispersion and diffusion coefficients is the natural movement between material. It's random in all direction and it varies geographically and over time. Near-field model is a model that's used to define the initial dynamics of a release. It provides the inputs necessary for a far-field model. Typically, with near-field models, you're working on the order of seconds and meters. Whereas if a far-field model has the order of hours and kilometers. Typically, when you think of oil spill modeling, you think of a far field model, as the far field model is what provides details on shoreline and surface oiling. Metocean data are your winds and currents. So when you're evaluating this spill risk, there's two parts of it. There's the probability of the spill and there's consequences. Spill probability is what oil or hazardous material may release here? What's the size? What's the duration? Where may it happen? What season could this happen? What's my environmental conditions? So those are determining the probability of a spill. The consequences are if that spill were to happen, what would happen to my shorelines, my habitats, my wildlife, fish and invertebrates? How oiled may they be? What about those socioeconomic resources or groundwater contamination if you're looking at a spill on land? Those are the consequences from that spill. When you talk about oil spill modeling and looking at your results from oil spill modeling, what you're looking at is the consequences from a spill to occur. So what's the difference between modeling for an analysis, such as an environmental assessment, or modeling for response? When you're doing an analysis, you're looking at impacts of oil spills on the coastline, ecology, looking at the consequences for a risk assessment, contingency planning, a net environmental benefit analysis. It incorporates a large data set, a combination of several models, and you're evaluating the environment and the pollutant sources. And typically, when you're doing this type of modeling, you're doing an ensemble approach, which is commonly referred to as stochastic modeling. Whereas emergency response modeling, which is typically called deterministic modeling, is short-term. It provides responders the need for robust and reliable modeling to predict the drift and weathering of an oil slick. It's for a particular date and time. You're integrating real-time environmental data for your metocean, as well as information on your pollution and your resources. And it's not only used for emergency response, it's also used for training and drill exercises. Going to pause this for a minute to have a little poll. So the question is near field modeling needed for subsurface releases? I'm going to give a minute for people to look at this and decide if they think it's needed or not needed. Okay, well, let's see. Let's talk about some of these processes again. So first, I'm going to start with modeling over land. So in this example, the schematic that I have a tank. It's released oil onto the land, and it's following the topography. As you can see here, I've got a hill, and the oil is flowing down. And then I have a depression where it's pooling, and then as that pool fills up, it continues following the topography. As it transports, you're going to have a drag to that based on the type of land, the land use. And you're going to have it continue traveling until it reaches a body of water, whether it be a stream, a river, or a lake. And as it travels, you're going to get a loss to evaporation. Once it gets into that river or stream, you're going to get downstream river transport. You're going to continue to get evaporative loss as well as oil loss on the shoreline. It's going to continue traveling down that stream or river until it reaches a lake, an estuary, or some other body of water. Once it gets into the water, there's a lot of other components that go on. So you can release it, again, directly into the water or from the subsurface, or it could travel from an event that occurs on land. Now in the water column, that water can form a slick on the surface. That slick can spread and it can be transported downwind and with your currents. Your wave turbulence based on your winds can cause entrainment to occur, meaning the oil on the surface gets mixed into the water column and you get oil droplets in the water. Those oil droplets can resurface and form a slick again, or you can have emulsification forming mousse and tar balls. If that oil does not resurface, it will stay a droplet in the water column. That oil droplet, the soluble component, the aromatic constituent, can dissolve into the water column, and you can get dissolved MAH and PAHs. Now, this dissolved component is the more toxic component of the oil. The dissolved component can volatilize into the atmosphere if it's in the upper wave mixed layer. And then if there's any suspended particulate matter, you can get absorption of the dissolved aromatics into that particulate matter. As well, that entrained oil droplet can adhere to that suspended particulate matter. If that causes a density change of that particulate matter, such as sediment, you can get settling down to the sea floor, and you can get sediment contamination. The oiled sediment, then any aromatics in that sediment, can then dissolve into the pore water, and you can get dissolved aromatics in the pore water of your sediment. Now, if that oil droplet, when it rises in it, or if it's as a surface slick, you also get evaporative losses. In addition to all these physics and the processes of oil weathering, you can also add mechanical cleanup and dispersant to treat the oil. Now, that oil on the surface is going to get transported downwind, and it may eventually become stranded on the shoreline. When it's on the shore, you'll have evaporation as well as degradation, just like you had in the water column. In addition, once it's on the shoreline, different shorelines have different holding capacities. The holding capacity tells how much oil can actually become stranded on the shoreline. So the rocky shoreline, for an example, can allow more oil to float back into the surface versus a marsh or wetland. The pore water of your sediment can also become contaminated with dissolved aromatics, as any of the aromatics from that shore oil dissolves into the sediment. Just like in the water surface, you can have mechanical cleanup from the shoreline. Now, subsurface releases, that could be from a well or pipeline. And what this does is it provides the details on oil droplet size distribution and the plume trap height. To get that, you need to use near-field modeling. Now let's go back to our poll. And let's see. So the majority of our group knew that near-field modeling is needed for subsurface releases. Nice job. So now when you're performing this near-field modeling, what it does is it gives the initial, so what I'm circling right here, this is that plume, and this is the trap height. And what that means is that is the point when the turbulence of that release of material from that well or the pipeline is going to cease, and that oil droplet or gas bubble is going to rise based on its own buoyancy. And the near field model is what provides you the details of that plume. So it gives you information on the droplet size distribution of the oil, the bubble size distribution of your gas, as well as that point of trap. You can apply subsurface dispersant to your oil as well. That's going to change the chemistry of your oil by affecting the surface tension. By changing the surface tension, it changes the droplet sizes that you will get for the oil, creating smaller droplets, thus not allowing it to rise to the surface as fast. To perform near-field modeling, you need to have 3D currents, 3D water and salinity data, bathymetry, and you need to know the ratio of gas to oil that's contained in the pipeline or the well, as well as the diameter of the release. Oil spill models. So for all oil spill models that are in the water, they're Lagrangian based. They utilize metocean data to transport the oil. So if you use inaccurate winds or currents, your transport will be wrong. And it's common for people to say that the oil spill model is wrong when they see this. Now, in this situation, it's most likely the metocean data that was used does not properly reflect the environment you're working on. The oils calculate weathering of oil based on the mass distribution, such that the mass is always conserved. Grids are then used to determine the thickness and concentrations. Grids are also used for your inputs, such as bathymetry, currents, wind, topography, and land use. Topography and land use are necessary for modeling on land. here's an example of what I'm talking about for thickness. So the model, being Lagrangian, these black dots represent a Lagrangian element, a spillet. This is what the model tracks, and it calculates the weathering over time. To get to thickness, you apply a grid over it. The cartoon picture to the left shows a grid being put on top of a Lagrangian element, a spillet. This black center is showing where that Lagrangian element center would be. A Gaussian distribution is then placed around this. What that does is you have a diameter of a spillet based on the spreading of that oil. The mass is then distributed based on a Gaussian distribution, so you have more mass in the center and less amounts out to the side. But the total mass sums to the total mass of that Lagrangian element. You do that for all the spillets. A grid gets put on top of it, and you figure out the mass in each grid cell. So in this case, I'm looking at this grid, this Lagrangian element here, and I've got about 7/8 of it here in this grid cell, where this one I have probably about 1/3. It takes this total mass, divides it by my area, looks at the density, and it comes to a thickness. And typically when you're trying to quantify how thick or how much contamination could be from an oil incident, you're going to be looking at it as thickness. The same is done for concentrations in the water column. It's important to note that if you put garbage in, your results are going to be garbage. The data quality affects your model results. But also the opposite to that is true. If you put reliable inputs, then your output is going to be reliable. It's important to remember that oil is not a single constituent. It's a mixture of hydrocarbons, ranging from short to long-chained hydrocarbons. It's made up of aliphatics, which are your straight-chained hydrocarbons that are typically more volatile than soluble. And then you have your aromatics, your MAHs, your PAHs. Your BTEX is part of your MAH. That's your benzene, toluene, ethylbenzene, and xylenes. Those are highly soluble, highly volatile, and moderately toxic. Your PAHs are 2-ring, 3-rings, 4-rings. Those are typically, your two-ring PAHs are typically soluble, less volatile, but more toxic. So when you're modeling, you need to look at all of the constituents, not just assume it's a single substance. Here's just an example to show that as the chain increases in size, so does the decrease in volatility and the decrease in solubility. So the more carbon that makes up that hydrocarbon, the less available it is to be lost to evaporation or lost to dissolution in the water column. Currents. There's 2D and 3D is most commonly used. 2D currents typically reflect surface currents. 3D currents break the bathymetry into varied layers. They're large in file size, and it's common that modelers may try to reduce these file size by reducing the time step or vertical resolution or domain. So it's important to remember if you're working with a 3D file and the file size seems very small, that you're ensuring that it actually has the data that's necessary for your modeling. 3D currents are needed for modeling from the seafloor. 2D currents are suitable for surface releases or releases occurring in the upper portion of the water column. Most 3D models, the first layer, the surface layer, is typically 10 to 20 meters. Rivers sometimes are simple 1D flow. Here are some animations showing currents. They're offshore currents, and as you can see, in the upper left, I have my surface. And then as you go, it goes deeper into the water column, 300 meters, 700 meters, 1,000 meters. You can see as we go down in the water column that the speed of your currents decrease. In addition, the direction of the currents also may change. This just shows the importance of having the proper hydrology to represent the area that you may be modeling. Winds, the benefits of using a meteorological model is it gives you spatial varying winds. As you can see near shore, your wind speeds change compared to offshore, where it's slower. If you use a spatial varying wind in your model, then you're able to incorporate that as part of the effects of the modeling. Just like weather. So is it going to be sunny? Is it going to be rainy? How much precipitation is there going to be? Your winds and currents are forecasts, especially when you're doing emergency response. There's many models out there that can provide the movement of water, hydrodynamics, and the movement of your wind, meteorological. Here's an example to show 3 different sources of data and how they can change the prediction of where oil may go. So this first plot that we're looking at, it's a single spill event, and I have wind from NOAA NCEP's North American model, and I have currents from the AdCirc group, which are tides. And I've outlined this trajectory in blue. Now I'm going to take that same exact spill event and just change the weather to have a different source for winds and a different source for currents. Now my source is from the US Navy. It's from their NavGen model and their HYCOM model, which incorporates tides and ocean currents. As you can see, the trajectory starts off going the same direction, but then it veers north and you have more northerly shoreline oiling. Now I'm going to take this for a third source. This comes from the NOAA NCEP global model, the GFS model, and their HYCOM model. You can see that this prediction shows oiling even further north. So when you're looking at this from an emergency response perspective, you don't want to look at just one source. Since you have more available data, you want to be able to understand where this oil potentially could go. So you want to look at the cumulative transport, which would look like this, that the oil could go in any of these directions. Then, once observations are available, you'd go and refine and determine the best source that predicts the movement of those winds and your currents. Now I'm going to talk about some model parameters, but before I do that, I have another poll to test you all. So this has to do with your model parameters. So these are not something that define your geographic area, but they're parameters that have to do with modeling. And which of these do you think are sensitive to your model results? Your wind factor, your dispersion coefficient, your wind factor and dispersion coefficient, your shoreline type, or all of the above. I'm going to give 1 minute for everyone to select their answer. Okay, let's go back to the presentation and we'll come back to that poll in a minute. So let's first talk about wind factor and drift angle. First, what are those? That's the fraction of wind that will transport that oil on the surface and at what angle it will be transported at. The angle comes into play due to Ekman transport from the spinning of the Earth. Typically, the wind factor, so that fraction of wind that will transport the oil on the surface, is between 3 and 4% of your wind speed. For the angle, if it's new wind after calm or wind from a new direction, so for an example, shifty wind, it's typically 0 degrees, meaning it's going to move directly downwind. However, if you have consistent wind blowing for about 6 to 12 hours, it's going to progress to a drift angle of about 20 degrees in the northern hemisphere. Below I have 3 examples. To the left, I have 1% wind factor with no angle, and then 3.5% at no angle. As you can see, only using 1%, it does not reach shore, whereas with 3.5%, it does reach shore. Now to the right, I also have 3.5%, but at 20 degrees. And you can see by applying that angle, it's not hitting the shoreline. Dispersion coefficients. This is the random motion in the water. The greater the value used, the greater distribution of the spillet's mass. So you'll get a larger area oiled, but it will be thinner. Typical values range from 0.1 meters squared per second for protected waters to 50 meters squared per second for storm conditions. To the right, I have examples at 3, 10, and 50 meters squared per second. As you can see, the larger the dispersion, the much larger the area, but it's thinner. If you compare it to the 3 meters per second, you'll see there's a lot of dark oil, but it doesn't cover the same extent as the 50 meters squared per second. Number of spillets. You need to have enough spillets for each time step when the oil is releasing. So remember, spillets are those Lagrangian elements. The more spillets that you have, the better resolution you'll have. Too few will not represent the oiling correctly. The reason a modeler might want to use less spillets is to improve the speed of the model running at. The less spillets you do, the faster the model will run. However, you have to be careful not to use too few so that you don't get inaccurate results. As you can see in the figure below, I have 20, 100, and 1,000 spillets. At 20 spillets, I've got a very spotty and disjointed plume. Where at 1,000 spillets, I've got a nice continuous plume that represents the thickness of the oil well. Model time step. Too large and your transport is not represented properly. Weathering calculations would also not be accurate if your time step is too large. As you can see in the figure below, I've got 15 minutes to the left and 2 hours to the right. At 15 minutes, I have a nice continuous plume, whereas at 2 hours, I've got a very blotchy, step-like, and doesn't look like it's representing the plume very well, similar to what looks like if you're not using enough spillets. Shoreline type. The holding capacity depends on your shoreline. The larger holding capacity, the greater mass retained on the shoreline and less on the water surface to continue to oil other shorelines. In the figures below, you'll see I have rocky cliff and marsh. The rocky cliff, you can see I've got a lot of oil that's still available to oil additional shoreline because the holding capacity of that shoreline is not able to take all of that oil. Whereas marsh, it has a larger holding capacity, and all that oil has become stranded on the shoreline, thus allowing less oil to further be transported. If that wind shifts and starts blowing to the east, we'll see that we have more oiled shoreline because there's more available oil to oil shoreline. I'm going to take a pause and go back to our poll. Looks like the majority of the group, by 77%, knew that all of the above, so the wind factor, your dispersion coefficient, and shoreline, were all sensitive to your model results. I'm going to go back to our slide. And now I'm going to rank them in order. So everything that we looked at, the most important is your metocean data and the selected oil, followed by your grid cell size, wind factor, dispersion coefficient, number of spillets, and your model time step. Now, shoreline type is listed on the bottom, but it does not necessarily mean it's the least sensitive parameter. It depends in the environment that you're working in. If you're offshore and there's not a lot of shoreline, then that's not a big concern. However, if you're in an estuary or a river or some area where there's a lot of shoreline, it's important that you have the shoreline classified properly so that the amount of oil that's becoming stranded on the shoreline accurately represents the type of shoreline that you have. Because if you don't have enough shoreline, for an example, that's marsh, then you're going to have more oiled shoreline versus what you would expect if it was a marshy shoreline. So let's talk about the steps to set up a simulation. First, you need to define the area of interest. You have a location, you have your resources, your habitats, and defining what's land and water. That's fixed for your case. Next, you have to define your scenario, your spill information, the volume, your product type, your time, your environmental conditions, your winds, your currents, and your model parameters. And this is the same regardless if you're doing deterministic modeling for emergency response or stochastic modeling for planning. Now, if you're doing planning, you have to take it one step further. You need to perform that stochastic modeling, which is just simply an ensemble of deterministic cases. So here in the upper left, you'll see I have 4 trajectories. What actually happens in stochastic modeling is you look at hundreds of deterministic cases and you pull them all together and you do a statistical analysis. And that statistical analysis gives you information on probabilities, minimum times, maximum thicknesses or concentrations, so that you can then evaluate under different environmental conditions what would be expected if a spill were to occur. And you just don't have to look at water surface. You can do this for shoreline. You can look at it for subsurface oil droplet concentration as total hydrocarbons, dissolved aromatic concentration, which is the most toxic for aquatic toxicity. You can look at the sediments, the hydrocarbons, and the aromatics in the sediments over time, as well as that's what's dissolved into the pore water. So going back to setting up the simulation, so if you're doing stochastic, you've run hundreds of deterministic cases, you've done that post-processing, and now you quantify, what is my worst case? That worst case could be the fastest to shoreline. It could be the one that oils the greatest length of shoreline, the largest surface area, the worst for the water column, what gives me the worst concentration in the water column for aquatic toxicity. So you define your worst case, and then you look at that deterministic case to further understand how those concentrations or thicknesses or your mass balance, the weathering changes for that under that particular case. A common question is, do I have to look at something seasonally, or is an annual stochastic simulation good? As long as you run sufficient deterministics as part of your stochastic analysis, the statistical footprint will be the same when you compare it to an annual compilation of 4 seasons. The benefit, though, of doing seasonal simulations is for planning. If you're putting together a response plan and you want to know where to position your response equipment, for an example, you would want to know how your conditions would be different under different seasons. In summary, to bring everything that we've been talking about, all of it's important, but in order to rank what's the most important that we talked about, the input data, your environmental and model parameters, you have to have good data in order to get good results. Second is, how do you understand and analyze that output? What's the skill? What's the user skill set to be able to do that? And lastly, the model's ability. So everything I've talked about today are models, which are OilMap and SciMap and OilMap Land. So OilMap and SciMap providing in-water column modeling, and then OilMap Land over land has these capabilities. And there are other models out there as well. And you want to be sure that whatever problem you're trying to solve, that the tool that you're using is able to address that problem. This concludes our webinar. Please come and visit. We have 3 more upcoming webinars scheduled. The next one is on October 13th, and it's focused on environmental sensitivity analysis, methods and examples focused on the oil and gas. And also visit peace.com to learn more about additional training courses. I'm going to open up the chat for any questions that anyone may have. And again, my contact details are there. And at the end of this webinar, we will be sending a very quick 5-question questionnaire asking you how this webinar was for you and how we could improve it for future webinars. So the question is, will we make this presentation available? Yes, for all of those that attended, we're going to be sending out a link so that you can look back at this presentation and hear the course. If anybody doesn't have any questions now, you can also jot down my contact details. You can send me an email if you think of questions later on. So the question is, do the models allow you to input shore type? Yes, it does. So you input your shore, whether it be rocky or gravel or marsh. So typically that information will come from observing satellite data or from ESI environmental sensitivity data or from field data. And you put that in either gridded or vector based, and then the model can read that to understand what type of shoreline you have so that the holding capacity is accurately reflected. And the next question is this software commercially available? And the answer is yes, they are commercially available. You can visit the website asascience.com, and there's links on the website that go over the oil spill models that I had mentioned. Again, if anybody thinks of any questions later on, please feel free to email me at nicole.malanathy@rpsgroup.com. There's a question, can the model handle complex shore types? I'm not quite sure what you're referring to as complex shore types. We have a classification of, I believe it's 40 different shorelines, and the most difficult piece of information is understanding the holding capacity of that shoreline. So if there's field data or information that defines your shoreline of what it can hold, how much based on the viscosity of the oil and how thick that oil can get to on that shoreline, then you can model that. We do have classification for about 40 different shorelines. I see that there's some more questions being written. You're welcome, John. I'm glad you found it informative. Yes, there's some experimental data. Trying to think of the exact source right now. Most of it comes from some work that Eric Gunlock had done that categorized different shorelines and the type of oil that there is and the viscosity and the thickness for that. And then there's a question on, does the model the atmosphere as well? The answer to that is yes. We actually have a coupled atmospheric dispersion model called AirMap. So it takes that volatilized and evaporated flux to the atmosphere, and it transports that hydrocarbon in the atmosphere downwind based on turbulent dispersion and calculates the concentrations. And you can evaluate this for total hydrocarbons as well as your BTEX so that you can assess your human health concerns for the environment. Thank you, Eduardo. I'm glad you found it informative. You're welcome, Fabrice. You're welcome, Robert. So when you're talking about the wind angle, so the question comes in about wind factor and the wind angle. To determine what the appropriate angle should be, you'd have to look at either experimental data as well as if it's during an actual instant, your observation. If you're doing it from a planning perspective, a lot of times you don't know what this will be. There is some experimental correlations that you can use based on your latitude, and you can correlate that to what your angle would be. And that can be used for planning. But during emergency response, typically you figure out what that angle would be based on the observation of the oil.